I just got this package, DHL. It's a miniVNA Plus, miniVNA Tiny Plus that I ordered from China. It came from Hong Kong, so I'm going to open it up and show you what's inside it. Okay, I got the bag open, and inside that is a box. So let's cut that open. And here is the box with the tape cut. Fairly well packed. Okay, and here is the little case that it comes in. So let's get this open. All right, and there is it comes with some calibration devices, a USB cable, 2 SMA cables, and the miniVNA Tiny. So, what this device is a miniVNA Tiny Plus, and I got the Plus because I noticed a video by Andreas Spieth, I think it is, who was doing it's a video from almost a year ago, in which he was doing some tests, and he pointed out that that he had bought a miniVNA Tiny Plus, and he bought it because that it had superior stability to the original VNA Tiny. So I looked for it, I found it on Amazon, and I ordered it. So now I'm going to hook it up and see how it works, and maybe do a little bit of a mini review. I want to talk briefly about getting the software for the miniVNA. The one that I ordered through Amazon came from China, Hong Kong. It arrived in about 5 days. It was very quick, expedited DHL service. I ordered it on a Friday and I got it on a Monday. So I said 5 days, 4 days. Very fast. This is a download page that I found going through the AliExpress website. They also sell this same miniVNA Tiny Plus. By the way, I decided to order it through Amazon because it came with some of the other accessories, including the calibration kit, which I'll talk about in just a second. But it has some websites where you can go. One of them is the East Chip miniVNA Soft, and the other is an MCU Lab pointer to that same website. What I found is, well, first let me just say that to get this to work, you have to download 3 things. One is you have to download Java. If say you're using Windows and you do not have Java running on your Windows system, you got to load Java first and get it working. Now, this particular website says that you have to use the 7U80. Well, here it mispronounces it as 7U8, but I found that my Java system is a later version than this, and it works just fine. So I'm going to guess that anything 7U80 or greater, it will of Java, that'll work. So you have to have Java working. You can do that from the Java website. You don't have to go through this site. By the way, this site is extremely slow, and I tried it at least a half a dozen times, and it would always time out before it completed the download. So I wound up going to the Java site to get Java. That works very fast. The second thing you need to have installed is the FTDI drivers. What these do is convert the USB connection to a COM port on your Windows machine. And once again, you need to download. But I tried these downloads, same problem, extremely slow. So I went directly to the FTDI website and downloaded their latest device drivers. And once again, those seem to work fine. Then, finally, you have to download the VNA software. It says click here. Well, same problem, extremely slow. However, if you go into a search engine and search for miniVNA, not minVNA, this is a misspelling, it normally is listed under VNAJ, and you're looking for the jar file. Now the jar file just means the Java archive. So you have to have Java installed before you can get this to work. Then you download this and it simply executes the operation. And then you can of course place a shortcut on your desktop or however you want to do it so that you can open it again in the future. But basically, I recommend that instead of trying to use these Chinese websites, that you just use the Java website. I can't guarantee this will work for everybody, so your results may vary, but it did work for me. I just downloaded the latest Java. Then I downloaded the latest FTDI drivers from the FTDI website, once again, the US website. And then I went and downloaded the VNAJ software. Now this I think comes from Germany, but it seemed to work okay, and it completely downloaded, everything worked first time. Now, after you've done this, you need to calibrate the miniVNA. So let me show you a quick way or a pointer to some good instructions on that. Here is a YouTube video entitled miniVNA Tiny Calibration Steps. It's put up by Unique Microwave. Now, it shows how to calibrate the miniVNA, which I did not show because this video does it as well as I could do or better. You have to, I'll point out one little anomaly you need to be careful of. You need to calibrate it once for reflections, and when you have done all three of these, in other words, you've calibrated the open, you've calibrated the short, and you've calibrated the load, then before you click on update, update will light green when you've finished all of that. Then click save before you click update and save that file. After you've done that, click update, and what will happen is a red flag at the bottom of your software will turn green. That does the reflection side. Then you have to change the mode to transmission and go back and create a transmission calibration file. For calibration of the transmission, you calibrate the open and the loop. And when you have done those two, you do not repeat these two. You do another open calibration and a loop calibration. And follow the instructions in this video and on the using your VNA software. You hook the DUT to the detector to do this, and you first you disconnect it to do the open, then you loop it back to do the loop, and then once again click save and finally update, and you'll be all calibrated. Here is a plot from the miniVNA Tiny Plus. At the top is the reflection coefficient. You notice that's the green up here. And at the bottom in blue is SWR. By the way, these can be changed if you put the mouse on this area. A checklist will show up, and you can pick what you want the green to show and what you want the blue to show. But what is instructive here, I think, is the relationship between return loss. Now, return loss, of course, is read on this scale from minus 80 at the bottom to 0 at the top. This is about minus 16, so this return loss is around minus 34 dB. You can find that a little more accurately by moving the mouse cursor there and then reading down here. That is at a frequency of 968 megahertz, and the return loss is minus 34.88. At the same time, the SWR is 1.04 to 1. So, let me point out a couple more things, and then let's take a look first at what it is we're measuring, and then at the relationship between return loss and SWR. So, this is 968 megahertz. This is the second harmonic and the third harmonic. Notice that the return loss is even lower at the third harmonic of this. Now, I will tell you ahead of time, this is an antenna designed to operate in the 900 megahertz cell phone band. So 968 megahertz is the, or 960 to 970 is the approximate operating range of this antenna. And you notice the SWR is very low here. As I said, it's 1.04. The SWR also is very low again at this point. It corresponds to this return loss, and so on. So let's talk a little bit about return loss and its relationship to SWR. If you are an amateur radio operator or you deal with antennas, I'm sure you're already familiar with the relationship of SWR and how it varies with frequency. You see that it starts out with a very high SWR, and then at the operating frequency it goes down to approximately 1 to 1. Let's take a little bit more of that in detail. Here is the miniVNA Tiny Plus, the red box, and the thing we're measuring, I have up here, but I'll move it down, is this antenna that operates. It says the frequency is 806 to 960 megahertz. Now, we can go over to the chart and look and see what the SWR would be over that range. It says it has 11 dBi of gain, and it's intended to be used in the GSM band. So let's now take a look at the relationship between standing wave ratio and return loss. Here is a chart that I prepared some long time ago. Notice that when the SWR, and by the way the V just stands for voltage, standing wave ratio, when it is exactly 1, what that means is that all of the power going into this end of the line is dissipated. In other words, nothing comes back. Another way to say that is the reflection coefficient is 0 and the return loss is infinite. Now, some people get confused with the term return loss. What they mean is that the signal, you put a signal into the line. Let's take a look at this. You put power into this side. If none of it returns, that means all of the return got lost. Or another way to put it is the loss between what you put in and what you get back is infinite. And that's what they mean by return loss. In other words, nothing comes back. It's like shouting into the darkness. If there's no echo, then the return loss is infinite. And then as you see, as the amount of reflection goes up, so that if half the signal is reflected, that's a return loss of 6 dB and a standing wave ratio of 3.5 to 1. Similarly, if everything is reflected, in other words, the signal goes down and everything comes back, that means the SWR is infinite and the return loss is 0. In other words, none of the signal gets lost. It goes in and it all comes back. So those are the relationships between these. And the miniVNA that I am using here is showing that on the chart that we saw earlier. Now, you can get the same kinds of indications with devices like this. This is an SWR meter in which one of the needles indicates the forward power and the other indicates the returned or reflected power. So the basic idea is that if all of the power that you put in stays in the line, none of it is reflected back, then the SWR will be 1 to 1. But as the amount of power reflected goes up, the SWR goes up with it. So it isn't necessary that you use a network analyzer or vector network analyzer to measure SWR. However, with a meter like this, you're only measuring at one frequency. The nice thing about a VNA is it allows you to measure a whole band of frequencies and see exactly how the antenna is performing or whatever the device is. So now for trick question of the day. If you have a transmission line that is leading out to your antenna, and you put 100 watts into this end of the transmission line, and 1 watt comes back, how much power is being radiated from the antenna? Remember, I said it's a trick question. The trick question, the answer is you don't know. The reason is you could just have a resistor on this end across the antenna that's absorbing all the power. You can't know what the radiated power is out of an antenna unless you actually go out to the antenna and measure it. All you can see from here is how much of what you send in gets reflected back. I've now connected a mini circuits splitter combiner. We'll look at the data sheet on this in a minute. Between the DUT into the S input, and then output number 1, or port number 1, is connected to the detector, and port number 2 is terminated in 50 ohms. So we're going to do a transmission test on this. In other words, how much of the power that comes into this port comes out of this port. And that's going to be done with the miniVNA. But before I get there, I thought it might be a good idea to caution those that are working with devices like this for the first time that you do need to be careful about two things. One is these devices do not tolerate DC voltage very well. And so you might want to consider getting a DC block. They look like this for SMA. They look like this for type N, and of course they make them for B and C as well as just about every kind. What they do is they block the DC. In other words, they have a capacitor in there, and they're designed to be fairly wideband. We might even look at the wideband characteristics of one of these at some point. But basically, they don't affect the frequency response very much, but what they do is block the DC. And of course that means that the very low frequencies are also attenuated because the size of the capacitor. The second thing that you might want to consider is putting some kind of attenuation on the output. Now these are SMA attenuators, but you can also get them in other types. This is a 30, in other words, a 30 dB attenuator. Might be able to see it. There we are, VAT 30 plus. You might want to consider using some of those, particularly on the output. Now, why would you want to do that? Well, the reason is that, for example, here is a mixer, and it's a passive mixer. It's a 3-port. In other words, you put a local oscillator into one port, you put an RF signal into the other port, and the third port is the intermediate frequency. In other words, it's the difference. It's also the sum and all the other components of a mixer. But this is a passive mixer. This is not passive. This is an amplifier. And you notice that on this side there is a connector for power and for ground. This is an amplifier. If you try to measure the transmission characteristics of an amplifier, you may wind up putting too much signal into the detector of the VNA. So you want to consider using an attenuator so that you stay within the ranges of the instrument that you're working with. Once again, that varies from one instrument to another, and I caution anyone who is using this kind of equipment for the first time to familiarize yourself with what the range of inputs that you can tolerate, and make sure you stay within those. If you don't understand that, find a mentor or someone who can help you. You might want to watch some of the YouTube videos by people like Mr. Carlson, who talks about how not to blow up your spectrum analyzer. At any rate, now we're going to do the transmission of this. So let's switch over and look at the software for the VNA, the miniVNA Tiny Plus. Here is the mini circuits data sheet for this splitter combiner. You notice that it's a 50 ohm splitter combiner. It's purely resistive, so it's passive. You don't need to worry about it amplifying the signal. In fact, it divides the signal, so the power actually goes down from input to output. It should work from DC to 4200 megahertz. In other words, it should be fairly flat out to 4200. And here is some performance data. Notice here on the left, it shows the frequency going from 0.05 to 4200 megahertz, and the total loss from S to 1 and from S to 2 is 6 dB. In other words, it divides the power in half, and that represents a 6 dB loss from the input to each of the outputs. So now let's look at the miniVNA and see whether it gets whether it comes up with comparable results. Okay, we are sweeping from 1 megahertz, from 100 megahertz to 3 gigahertz, which is the maximum range of the miniVNA. Maximum at the top. It can go down to a megahertz at the bottom, but we're starting at 100 because it just expands the scale a little bit. So at the top is the transmission loss. Remember, we're now measuring transmission, and down here in the lower right-hand corner, you see it now says transmission instead of reflection. And you notice the phase changes because of the frequency. But basically it is completely flat. Well, relatively flat. And if you notice on the left, this is minus 8 dB, this dotted line, this white dotted line here. So we are getting about -6. Now let's check that by putting our cursor on one of the low points, and we look down here and we see we're getting -6.64 dB. Now let's go to one of the high points, and there we're getting -5.5 dB. So the splitter combiner is operating over the range from 100 megahertz to 3 gigahertz, and is dividing the signal into approximately half on each port. So once again, this is a transmission measurement, not a reflection measurement. Now let's do a reflection measurement on this same device. We don't need to change anything, except we need to go down here and change transmission to reflection and run a scan again. Okay, you'll see that the reflection coefficient, or the reflection loss, is here. Let's go to SWR over here on the blue trace. They're basically parallels of one another. By the way, if you want to, you can move the traces, like this one or this one. If you want to expand the trace or move it, etc., you can do that by clicking in the margins. So this is the SWR, and you notice the SWR is the highest, where the reflection loss is also the highest. In other words, when there is the most reflected energy is also when the SWR is the worst. Now when you get out to the highest frequency, you'll notice that the SWR starts to approach, well, let's see what that is. Okay, the SWR is 1.89 to 1 out there, and the return loss is -10 dB. So in other words, a lot of the signal is reflecting back to us at that frequency. So this shows how you can use the miniVNA to do both reflection and transmission measurements. Now, if we wanted to, we could turn around and hook the miniVNA backwards on this device. We are measuring, essentially what we have done is we've measured S11 here, and then over on the transmission side, we measured S21. So you can get the full range of scattering parameters for a device using this miniVNA Tiny Plus. So I've been impressed with it so far. I'm going to continue to do some more experiments with some other devices, and then at the end I'm going to do a second video that will show how I could have done some of these same measurements with some of the other equipment that we talked about back in the introduction. Now I have switched to a Barker and Williamson TVI filter. Now Barker & Williamson was a manufacturer of ham equipment and communications equipment after World War II until, I'm not sure if they're still in business, but at any rate I bought this, I'm guessing, in the 70s. TVI just means television interference, and ham radio operators before the switch over to digital often had a problem because the TVs of the day, the old analog TVs, many of the cheaper ones, and as the years went on they tended to get cheaper and cheaper, didn't have adequate shielding against RF. And so the burden fell on amateur radio operators to reduce the amount of energy that they transmitted that might interfere with television. And one of the ways to do that was with one of these filters. So you put it in the line, the transmission line to the antenna, and what it did was it cut all of the frequencies above about 40 or 45, 50 megahertz, which is sort of the transition region between the ham bands, usually 30 megahertz and below, and the TV bands, generally 55 megahertz and above, or 54. So I'm doing a transmission test using the miniVNA. So let's go over and look at how it looks on the software. Now I've reduced the span, that is the distance from the left to the right in terms of frequency, to 1 megahertz on the left and 50 megahertz on the right. Now, I indicated that what you want is you would like to have at least 40 dB of attenuation at 50 megahertz. Well, this is 41 dB right here, and you see that's where we are at about 47 or so megahertz. At the top is the transmission loss, and let me move this down as far as I can. This is 0 at the very top, and you see there's a little bit of trace here, and then it goes to 0 at about 2 megahertz and stays there all the way up to about 35 megahertz, and then it falls off pretty good. So this was a pretty good filter for the day. Now they're a little bit of an artifact because digital television is nowhere near as susceptible to TVI. So these days there is not a lot of market for these TVI filters. But nonetheless, it's I wanted to try one because it's something that ham radio operators use fairly often back in the day. I'm going to, I think, divide these videos into another part, because I'd like to do some more tests with the miniVNA Tiny Plus, but I am sort of running out of time. So what I'm going to do is one more experiment. I'm going to do a reflection. Oh, by the way, the blue trace is the equivalent series resistance. And notice that it remains around 72 ohms until it gets out here where the band stop begins, and then it goes up dramatically. So let's switch over and take a look at a ham radio dummy load, and then we'll try to close out this part and move on to a part 2. I've now set up an MFJ 300 watt dry dummy load. This is the model MFJ 260. Once again, it's from the the 70s or 60s. I can't remember when I bought this. I was first licensed back in the late 50s, early 60s as a novice, and later upgraded to general and advanced and so on. So what, of course, this is designed to do is to absorb the power from a transmitter so that you can test without radiating a lot of RF energy out through an antenna. And as it indicated, it operates up to 300 watts. Of course, with the miniVNA, we're putting, I'm not sure exactly how much, but maybe milliwatts. So let's take a look at, oh, by the way, what we should expect to see here is reasonable SWR, and therefore a good return loss. That is a high negative number on the return loss, up to at least above 30 megahertz. These were generally intended for HF use from about 2 to 30 megahertz. So I'm going to run it from 1 megahertz up to 200 megahertz, and let's see how it performs. Okay, at the top is the return loss, and you notice that the return loss is about minus 16 dB and remains relatively flat out to about 100 megahertz. This is a 100 megahertz right here. Similarly, the SWR remains below 1.39, that's this line, out to about the same point, at which point the SWR begins to go up, and if you use SWR of 2 as kind of a good boundary condition, at least for modern transistor transceivers, then you're probably at this point, which is about probably 170 megahertz, and you notice that the return loss is beginning to fall off. In other words, this dummy load is beginning to reflect more and more power as we get out past, well, in this case, actually about 100 megahertz. So, perfectly adequate for testing transceivers, but not really a high-performance dummy load. Okay, where are we going to go from here? Well, what I would like to do is to perform some tests on the miniVNA itself, look at a few things, and also do some tests on some equipment that I have, like some DC blocks and some other things that may or may not be of much interest, because they're really more just stretching the capabilities of the miniVNA Tiny Plus. But mainly what we're going to try to do is to characterize the miniVNA Tiny Plus a little bit in the next part, and perhaps look at, compare it to a few alternatives. And we're going to be using things like attenuators and DC blocks and so on, just as test vehicles. So I hope you'll stay tuned for the part 2. And actually, this is a 3-part, if you consider the introduction, the 2 RF 2-port measurements as part of this, then it's really a 3-part video. But at any rate, part 2 coming up. Look forward to it, I hope. I hope you did enjoy this. And in the meantime, have a nice day.